Okay, so here it wants us to match the pendulums right here and the springs over here on the bottom left and the graphs at the top. So if we look at this first graph, we have displacement on the y-axis, time on the x-axis. Notice that the equilibrium position is at 0 centimeters and that our amplitude is going to be the distance from the center to either a crest or to a trough. Okay. If you look at graph 1, notice that we have a wavelength in 0.5 seconds. So we have 1, 2 wavelengths per second. So it has a frequency of 2. Notice that this one only has 1 wavelength per second, just like the last one. The main difference between the second graph and the third graph is that the second graph has a greater amplitude. So if we analyze the springs first, I noticed the first thing, spring A, spring B, and spring C all have a spring constant of 20 newtons per meter. Since we know that time period and therefore frequency are based on 2 pi times the square root of m over k, the only things that are going to affect the time period and frequency of a spring are going to be the mass and the spring constant. Well, all of these spring constants are the same. Therefore, the smaller m is going to give us a smaller time period and therefore have the highest frequency. So looking at the 3 springs, we notice that spring A has the smallest mass, will have the smallest time period, and therefore the biggest frequency. Since this graph has the most frequent wavelengths, it must represent spring A. If you look at springs B and C, they both have the same mass, 2m, so they're going to have the same frequency. Which makes sense, the 2 remaining graphs have the same frequency. So they have the same mass, they have the same spring constant. Really the only difference here is that spring C has a greater amplitude. It goes out further than spring B. Since the second graph represents a wave that has a greater amplitude compared to the last graph, this graph must represent spring C. And therefore, since this has the same frequency as the second, but a smaller amplitude like spring B, this must represent spring B. Now looking at the pendulums, we have A, B, and C. Notice that A and B are the same longer length and that C is the shortest. Frequency and time period for a pendulum is based on 2 pi times the square root of length over the acceleration due to gravity. So, assuming that we're on Earth, the only thing that's going to affect it is the length. The shorter the length, the shorter the time period, and therefore the higher the frequency. Since pendulum C is the shortest and has the smallest length, it will therefore have the smallest time period, and therefore the first graph, which is more frequent, will represent it. Now, if we look at the next two, A and B, they have the same length, so they're going to have the same frequency. But A has a greater amplitude. Okay, notice that the amplitude here is 15 degrees, while the amplitude for B is only 7.5. Remember, amplitude is measured from the center or equilibrium position to one side. So the equilibrium position would be right down through the center. Anyway, since pendulum A has a greater amplitude, it must be represented by the second graph. And that means that pendulum B must be represented by the third graph.